Hello, it's Mr. Norris, and in this video I'm going to teach you how to think about logarithms. Before we start working with logarithms, we really have to understand what they mean. Let's relate logarithms to some of the algebraic tools you've learned in the past. We'll start with some simple equations. Since you were probably in middle school or even as early as late elementary school, you've been able to solve equations like this: x minus 2 equal to 4. The goal, as your teacher probably told you over and over again, was to get x by itself. So to do that, we do the sort of opposite operation idea, where since we're subtracting 2, we add 2 to both sides, and we get x by itself. We find that x is equal to 6. Easy enough. Or maybe we're considering an operation like multiplication, where you had 3 times some value x equal to 9. Again, you would employ this idea of opposite operations. Since it was 3 times x equal to 9, you would divide both sides by 3, and you would get x equal to 3. In the top, we've seen a situation where we had to add a number to both sides, or maybe we had to divide both sides by some number. You've also dealt with numbers, unknown numbers raised to some power. For example, x to the second power equal to 16. And you learn to take the square root of that. So I take the square root of both sides, it would get rid of this second power, and I would ultimately get x equal to positive or negative 4. And more recently, since you've learned about fractional exponents, and as well you've learned about taking cube roots and fourth roots and fifth roots, I could take something like x to the third equal to 8, and I could take the cube root of both sides, and I would get x equal to 2. So the point is this: in all of these situations, you clearly know how to get rid of the value x. Let's take all these situations and maybe put them off to the side for a second. Suppose you had something like 2 to the x power equal to 4. How would you be able to solve that? Well, I certainly can't divide both sides by 2, so that's not going to work, because 2 to some power doesn't mean that I can simply divide both sides by this base. So division isn't going to work. Sometimes students think that they can look at this and take the square root of both sides. But let's remember, this isn't the same thing as x to the second power equal to 4. This equation and this equation are very different. I may be able to take the square root in this situation and get x by itself, but I'm not going to be able to do that here. So for now, let's think about what this is saying. 2 to some power x is equal to 4. So 2 to what number is going to get me 4? Well, if I think about it off to the side, 2 to the second power equals 4, because 2 to the second power is 4. So that tells me, just by looking at this, that x is equal to 2. So sometimes, even if I don't have an operation to solve this thing, I can still go back and figure it out with guess and check. Let's look at another situation like that. So maybe I'm thinking about 3 to what power is going to give me 9? Well, I'm thinking 3 to the first is 3, that doesn't get me 9, and 3 to the third is 27, and that doesn't get me to 9, but 3 to the second power gets me to 9, so clearly this is another situation where x is going to equal 2. Okay? Let's consider something like 3 to the x equal to 10. And let's try and solve that by inspection. So I know that 3 to the first power is going to be equal to 3. That's not equal to 10. So that's not going to work. So let's try another possibility. So maybe it's 3 to the second power, but that's going to equal 9. So that clearly doesn't work. Or maybe we want to go one more up. Maybe it's 3 to the third power, but that equals 27, so we've gone too far. Our x, if 3 to the second gets us 9, and 3 to the third gets us to 27, then 3 to the x must be some power between 2 and 3, but how do I get to that? I certainly can't divide here. I certainly can't take the square root. How can I get x by itself so that I can solve this equation? That's where logarithms come in. So we're going to talk about how we could use logs to solve this problem, 3 to the x equal to 10. Let's try and write that out in words. I'm ultimately asking 3 to what power gets me 10? We're going to take this equation and we're going to rearrange it into a log. To see how we move these parts around, and by parts I mean we're ultimately dealing with a base 3, a variable x that's acting as an exponent, and a value that it's equal to, a constant 10. So let's go ahead and write those in different colors so we can see the parts of it. So we have some 3, it's raised to some value x, and that's ultimately going to be equal to some constant 10. Okay, now I have those, and now I'm going to rearrange it. So I'm going to write out log. Oops, let me do that in black. And I'm going to put in 3 here. So I'm going to put in a small 3. So log base 3. I'm going to put in 10 here. And I'm going to set that equal to x. Okay, so I've taken that original exponential equation at the top, and I've converted it into a single variable logarithmic equation. There's no way that you can find this value in your head. So we're going to have to do, at least not this particular logarithm. There will be some logarithms, as we will see later on, that you can calculate in your head. But this one you're going to need a calculator for. So in your calculator, you're going to put in log of 10 base 3. And if you need help doing that, I can come around and show you. And you're ultimately going to get that x is equal to, and you're going to get that that's right around 2.1. Let's go ahead and test that out. So if I raise 3 to the 2.1 power, what do I get? Now that I'm doing this video, I'm going to pause it and I'm going to try and put that into my calculator. I get out something really close to 10. When I put this in my calculator, I got 10.04, 10.05. That's okay. It's going to be really, really close to 10. The reason that we didn't get exactly 10 is because we decided to round this value of x. If we continued putting out tons and tons of decimal places, our answer over here would be far more accurate. But that's okay, it's perfectly acceptable to round. The big idea is that we can take an exponential equation, we can rewrite it as a logarithm, and then we can take that logarithmic equation, put it into our calculator, and get a value of x that works. With practice, it's going to be very important for you to learn how to make these conversions. To learn that the base of an exponential equation is going to be this base of your logarithm, and that we take whatever goes in this place and also enter it into this part of the logarithmic equation, and that the power of the exponential equation is going to come here. So it's going to take some practice, but soon you'll be able to take something like this and turn it into that. Let's think a little bit more about what logarithms are saying. So, in our last example, I said that you would need to use a calculator to figure out what a particular logarithm was. And sometimes that's going to be the case because it would have been impossible for you in that last example to really figure out, hey, this answer is 2.1. At the very least, it would have taken a lot of guess and check. But there's some logarithms that we can figure out. So let's practice some of those. So suppose I have log of 25 base 5. Let's think about what that is actually saying. So this is saying 5 to what number is 25? And you know that. 5 to the second power is going to be equal to 25. So this value, log 25 base 5, is simply equal to 2, because 5 to the second power equals 25. Okay, let's try another one. So maybe we want to consider log of 16 base 2. Okay, so how would I write that? Log of 16 base 2. This is saying 2 to what power is 16? And if you think about that, you know that 2 times 2 is 4, 4 times 2 is 8, and 8 times 2 is 16. So that's 2 times 2, that's 4, 4 times 2 is 8, 8 times 2 is 16. So 2 times itself 4 times gets me to 16. In other words, 2 to the 4th power is equal to 16. So that means that log of 2 base 16 is going to be equal to 4, because 2 to the 4th power is 16. I would encourage you to pause the video and think about this next example. Okay, that's just saying 10 to what power is 100? And you know that 10 to the 2nd power is going to get you 100, because 10 times 10 is 100. So this logarithm is going to equal 2, because 10 to the 2nd power gets me 100. And as a very important side note, there are some things that we assume in mathematics because we see them so often. The classic example, which you've learned about, is that there are many different kinds of roots. In your entire, probably, career in high school, middle school, you've seen stuff like square root of 4, that's going to equal 2, or square root of 16, that's going to equal 4. But you've learned that there are things called cube roots. So we might take the 3rd root of 8. So this entire time, you've been writing the square root of some value without writing a 2 here. Because we see the square root so often, we know that if we take something like the square root of 36, we don't have to write that 2 there because we see that square root so often. When in reality, sometimes we might choose to use it. Sometimes we might choose to say square root of 36 with a 2 right beside the radical sign. There's a similar situation with logarithms. So, if you have log of some value, log of some value base 10, that's going to just be equal to log of some value base 10. But what's the difference between this thing and that thing? Well, over here, we chose not to write the 10, and that's okay. It's perfectly acceptable if you're taking some value base 10 to exclude the 10 from this part of your logarithmic equation. So if you see something, say log 100, and you don't see some value down here, you can assume that smaller number is 10. It's a very simple idea, but it's something that you need to be very careful about when you're doing problems. So we've learned what it means to have a logarithm. But how can we actually use logarithms to solve single variable equations? So let's look at one. Maybe I have 10 to the x plus 2, and I'm going to set that equal to, say, 100,000. So that's 1 with 5 zeros. Okay. This gives me an opportunity to write this as a logarithm. So I'm going to, in my case, go ahead and change this into different colors. So 10 to the x plus 2, and I'm going to set that equal to, I don't know, 100,000. So I'm going to write that in and convert it into my logarithm. So I want log of 100,000 base 10 equal to x plus 2. And I remember that if I wanted to, I don't even really need to write this 10, because if I didn't write this 10, the reader would just assume that it was not here. And they would assume that it was base 10. Okay, so I can either put this in my calculator, or I can ask myself 10 to what power gives me 100,000. Oops, just realized I left off a 0 there. Sorry about that. Okay, so 10 to what power gives me 100,000? I put that in my calculator, I do it in my head, and I realize that that's going to be 5. So now 5 is equal to x plus 2. Really simple equation to solve now. I can just subtract 2 from both sides, and I'll get that x is equal to 3. So without logarithms, I might have struggled to solve this equation. Let's look at another example on this side of the screen. Suppose that I wanted to solve 2 plus log of x base 3 equal to 5. So when I see something like this, the very first thing that I want to do is get this log by itself. It's not entirely different from the way that you solved equations in the past. In the past, your goal has been to get that x by itself. That's still the case when you're solving equations that contain logarithms. So first let's get the 2 out of the way. Let's subtract 2 from both sides. Alright, so now I have log of x base 3 equal to 3. So I think I want to convert that now into an exponential expression. So I'm going to take, I realize that this is saying 3 to the third power is equal to some unknown number. So if I want to convert that into an exponential equation, that's saying 3 to some power 3 is equal to x. Now it's just simple computation. 3 to the third power, 3 times 3 times 3, is going to get me 27. Okay? So what's the big difference between this equation on the left-hand side and this equation on the right-hand side? Think about that for a second. So on this side, we had to take an exponential expression and then we had to convert it into an equation with logarithms. Whereas on this side, we had to take an equation with logarithms and convert it into an exponential form. So the point of this slide is to see that sometimes to solve equations, you have to go from exponential to logarithmic, and in other equations, you have to go from logarithmic to exponential. So it's all going back to this rule that if the log of c base a is equal to b, then I know that a raised to the b power is going to be equal to c. So it's going to be very key to go back and forth between these two formats. In the next slide, I'm going to give you one more example, and then I'm going to conclude this lesson. So let's suppose that we have 5 to the times 10 to the 2x equal to 60. So again, my goal is to get that x by itself. So first, I'm going to divide 5 by both sides. So since it's 5 times this value, I'm going to divide 5 by both sides. So I'm going to divide by 5 on my left-hand side, divide by 5 on my right-hand side. Now I'm going to get 10 to the 2x, since these 5 cancels, since those two 5s cancel, and I'm going to get that equal to 12. Now I'm at a point where I can convert this to a logarithm. So I'm going to say log of 12 base 10 is going to be equal to 2x. I'm going to throw this left-hand side into my calculator, and I'm going to get, it's roughly around 1.08. So all of this, if I put it into my calculator, comes out around 1.08. Another way I could say that is 10 to the 1.08 power gets me to 12. Okay? So I have that left-hand side, and now I'm just going to rewrite my right-hand side. Pretty easy at this point. Now I just divide by 2. And 1.08 divided by 2 is 0.54. The reason that I wanted to show you this problem is that at some points it's very tempting to stop solving once you found out what this logarithmic expression on the left-hand side is. In other words, once I found out that log of 12 base 10 was 1.08, it's very, very tempting to stop. But you have to remember, you can't stop solving your equation until you get that x completely by itself. So in this video, we've discussed the idea of what a logarithm is and what it helps us do when it comes to solving single variable equations.